Hi everyone, and welcome back to the Weekly G. This week I just wanted to talk about two things that I thought about when I was doing last time's Weekly G about hurricanes, Weekly G number 6. And so I just thought of two extra other things that were kind of interesting, and I wanted to talk about those. So the first thing is I wanted to mention about how climate change will affect hurricanes, and so that's the first thing. And the second thing is I just wanted to give some details about the Coriolis force, since I kind of glossed over that at the end. So climate change is, I'm first going to talk about climate change just very briefly. So climate change, which people usually call global warming, is a change in the typical weather of the Earth. And one of the things that it's expected to do is we think it's going to make weather more volatile. So in particular, storms like hurricanes are going to be more common and more devastating. So I just wanted to say a couple of words about why that might happen. So before I begin, I want to put out a caveat. The model I'm presenting is just, something I thought was reasonable. It's not something I've actually tested at all. So, I haven't read about this, I haven't tested about this. It's just I thought about stuff based on last week's Weekly G, and I thought this was kind of interesting. So, if you recall from last time's Weekly G, this is how a hurricane works. You've got some warm water down here, and you have a region of low pressure. A region of low pressure. What this does is it makes winds flow from relatively high pressure regions towards this low pressure column of air. And this air is very warm because this is all happening in kind of the tropical oceans around the equator. It's warm and it's humid, it's wet. And what happens is this warm wet air gets carried into this low pressure region where then it goes up. And up at the top, you have kind of this cool, dry air. And so the warm, wet air that's coming through here gets carried up into the atmosphere where it condenses into water, releasing latent heat. And this maintains this low pressure column of air, keeps it warm, which is the same thing as low pressure, and this engine, essentially, is what causes a hurricane. And so that's just a review, and now about global warming. I gave a number over here, which last week I said was 80 degrees Fahrenheit. Basically, if the water is at 80 degrees Fahrenheit, then if you have like a low pressure air column seed, which I think actually comes from like tropical storms in Africa, you can kind of continue this process. Like that's kind of like the cutoff value for hurricanes to start. So the idea is that there's a lot of little instabilities, a lot of little storms coming off of Africa that could potentially form into hurricanes. But a lot of the time the water isn't warm enough. Like you can't constantly be bringing this warm, wet air into the hurricane if the temperature of your ocean is not high enough. But the idea is that if you have global warming, then a lot more of these kind of low pressure regions that are seeded by tropical storms in Africa, a lot more of these things are going to turn into hurricanes. And the winds around them are going to grow even more because the oceans are warmer. So you can see how like only a 1 or 2 degree change might actually make a difference in whether a hurricane can continue or not. If you take in this idea of an 80 degree Fahrenheit kind of cutoff temperature, plus or minus, if there's some sort of cutoff temperature, raising it so that most of the ocean water is above this temperature most of the year means you can get a lot more hurricanes. So again, I just made this up based on what I told you about hurricanes. I don't actually know if this is correct or not, but I think it gives a good idea of how difficult it is to predict how climate in different parts of the world will react to small changes in our atmosphere. So just 1 or 2 degrees can be the it can be the difference between some choppy weather and Hurricane Sandy. So that's all I just wanted to mention a little bit about climate change, since that's relevant to everyone. And now back to kind of some more normal science. So last time I talked about this, how hurricanes get their direction, and I said that was due to the Coriolis force. So if I'm looking at this from a bird's eye view, I have a low pressure region that I've marked in green, and I'm going to have green winds coming in over here. And the reason the winds are coming in, remember, is because it's a low pressure region in the middle, it's a higher pressure region outside, and so air flows from high pressure regions to low pressure regions. And remember how I said the Coriolis force actually makes this kind of spiral this way? It spirals this way in the northern hemisphere, and it actually spirals the other way in the southern hemisphere. And the reason this happens, as I just said, is the Coriolis force. And what the Coriolis force is it's not actually a real force. There's not any law of nature that says there needs to be a force that makes things spiral this way, but it's a consequence of the fact that the Earth is rotating. So if you have a rotating Earth with some angular momentum omega, so when I draw the arrow that way, it means that the Earth is rotating this way. And imagine having a little particle over here that's traveling straight down. You can imagine that as the Earth rotates kind of, to the right, and the particle travels straight down, it's going to end up effectively, let me do this in red, it's going to end up effectively kind of curving off a little bit from in the point of view of someone sitting on Earth, right? If you're not like stuck to the ground, then if you move down on the Earth and the Earth rotates a little bit, you're going to end up a little bit to the left of where you actually were. And that's the basic idea behind what the Coriolis force is. And we can express this whole thing mathematically as this vector equation, which is that the Coriolis force is equal to negative m omega cross v, where omega is this angular momentum over here, and v is the direction of the velocity on Earth. So let me give you an example of how, let me give a little more concrete example of how this actually works out. So here's kind of like the top quarter of my Earth, here's the bottom half, and here's my omega, which is just indicates the direction that the Earth is spinning. And here's my little particle, and let's say I'm traveling south, right? Then what direction? So yeah, I'm traveling south with some velocity v. So what direction does the force exert on me? Well, if you do your cross product rule over here, you do your right hand rule, you put your, one thing in the direction of omega, the other thing in the direction of v, and the third finger, or you curl your hand, and you get the direction of the force. In this case, don't forget the minus sign that I put over here. You'll end up getting that the Coriolis force points out of the page. If you're used to this kind of notation, the arrow is pointing out of the page. And if you map this back to this original image that we had over here, that's equivalent to saying that this guy curves off to its left. So let's do this again, but have the particle be going up instead, right? If the particle is traveling north, you've got a v over here, you got an omega over here. Do your cross product, and you'll find that the Coriolis force points into the page. Does that make sense? Yeah, so you see, this ends up causing it to spiral around the other way. So that's kind of cool, and this actually explains the why the hurricanes rotate in different directions on different parts of on different hemispheres of the Earth, right? So, you got this angular momentum pointing over here. I'm not going to do this out for you. You can try it yourself, but if you make a similar thing, you'll see that the Coriolis force is going to cause these winds that are going towards the low pressure region over here to spiral in the opposite direction from the northern hemisphere. So in the northern hemisphere, it goes counterclockwise. In the southern hemisphere, it goes clockwise. Okay, so that's kind of neat, right? I guess I just wanted to add one more thing about what the Coriolis force can do for you. What the Coriolis force also does is at the end, it stops the wind from collapsing into the very middle, of this central part. Oops, that's not what I meant to do. Ends up, so this middle central green part over here, the Coriolis force also stops the winds from actually entering into here. So let me draw you an example over here. So I've got my low pressure region over here. And let's say for a moment that I've got my, I have my winds. I'm going to draw my winds in red here. And they're circling about this way. So up here it's going that way, it's going this way, going this way. Now it's going that way. And the idea is that, I'm going to use orange for force. The idea is that there's kind of a pressure force that's pushing the winds into this low pressure region, right? The green is the low pressure region, and so the orange indicates that, the molecules inside of the air that are forming this wind are going to be pushed inwards. But if you look at the Coriolis force on the wind that's spiraling this way, you'll actually find that the Coriolis force exerts a force opposite this. If the winds are circling around in this direction, the Coriolis force is very interesting. It actually counteracts this inward pressure force. And so when this orange, so until you get into the very center of the hurricane, the orange force is usually winning, so the pressure force is causing winds to blow towards the center of the hurricane. But when you get into this, kind of special radius, then the Coriolis, you're traveling fast enough, and the Coriolis force is strong enough that you can actually balance this pressure force. And I think, I'm not 100% sure, but I believe this is what creates the eye of the hurricane, right? So when you see hurricanes, you have this little eye in the middle, and all of the winds are swirling around outside. But there's a place that is very, you can guess what it would be inside of the eye. It's going to be very warm, it's going to be pretty wet, but it's, because of the Coriolis force, it's actually not going to have any strong winds. And so I kind of like that. I kind of think this is interesting because people always say, if you're very calm and when there's lots of turmoil, things going around you, then you're the eye of the hurricane. But I think that's kind of funny because the eye of the hurricane is actually what's causing the whole hurricane in the first place, right? It's the low pressure region. Okay, well, that's all I have for you today. So see you next time.